Hello everyone. Today my presentation topic would be freezing paleosols in a drone-based photogrammetric model. My study area is in the Bighorn Basin, Wyoming. So let's first have a look at the basin. So this is the Bighorn Basin in the northern Wyoming, and our study area is indicated by this yellow star. And our study interval is the early Eocene Wellwood Formation. Is 1 million years younger than the Paleocene-Eocene thermal maximum. And in our study interval, there are two hydrothermals, namely H1 and H2. For the Paleocene sediments, they are just below the boundary sandstone that separates Paleocene from Eocene. Here you can clearly see at least 4 cycles, like here 1, 2, 3, 4. Within each cycle, you can see a whitish catalytic deposits at the base, and also reddish-orange paleosols on the top. So those cycles have been described in the previous work, and they are divided into 2 phases. So the lower one is known as the washing phase, and that was developed in the channel instability stage, where channel tend to walls here and there depositing catalytic deposits. The other phase is the overbank phase, which is featured by the very developed paleosols, as you can see here, also here. So those paleosols are developed in the distal floodplain of the stage where the channels are super stable. Here we show the Eocene sediments. They have similar cyclic patterns as those Paleocene ones, but the colors are much redder and sometimes purpler. You can see those trenches. They are dark, deep, and wide to see the fresh rock surfaces. So when we are freezing those paleosols, we know how this look like on the fresh surfaces. Okay, here we make the drone model. As you can see, there are many lines. We first start with those black contour lines. They are 10-meter contour lines. You can also see those colored lines. They are following the top level of the paleosols. When you also see those sandstones, and when they appear, it's difficult to identify the paleosol layers because of the interference of channel processes on the soil development. We also make those digital sections to compare the thickness from one place to another place. Here we show how they look like in a composite stratigraphy that is comprised of two French sections. You can see the thickness varied in 1D in this stratigraphy. It's about 300 meters, and the average thickness of the cycles are 6.8 meters, with a standard deviation of 2 meters. Now we are going to zoom in the cycles from H to N here, because they have a larger lateral coverage, and here you can see the distribution of one cycle. It can be quite scattered. Sometimes it may be less. Yes, also the cycle K is overall much thinner than cycle L, because these squares indicate the average numbers. And those 7 cycles have an average of 7.3 meters. Now we show the digital sections I have mentioned in the previous slide. They are shown in this direction. You can see they vary quite significantly in the latter. Sometimes you may see a thinner cycle is directly overlain by a thicker cycle. That may indicate compositional stacking. We also want to investigate the spatial continuity of these cycles, so we apply the variogram analysis. Variogram is to measure the similarity between 2 points, like those 2 points, over a distance of h. But when this h increase by some moment and at some lag distance, those 2 points are not related to each other anymore. This lag distance is called range. So in a 2D setting, there is a long range and also a short range. Okay, now we apply this method on the cycles, on the thickness of cycle h first. We identify a long range in the azimuth of 5 degrees, and that's about 1.5 kilometer. Then we also find a short range in the 95 degrees, that's just perpendicular to 5 degrees. We also see some cyclicity, these up and down patterns, also the so-called Hall effect in the other directions. Okay, now we populate these methods to the other cycles. So here we show the long range, all set to 0. Here we have the short range. We can see they have different values and also they have different slopes. That means each cycle has a different feature. If we combine the short range and also long range information and also the azimuth information, we obtain those eclipses. And they have an average azimuth of 1 degree. Interestingly, we have an average paleoflow direction of 4 degrees, as we measured in the dunes, crossbeds, also some lateral gravitational surfaces in the field. So those two numbers are quite similar. Then we have to speculate whether there is a certain correlation between them. Now we apply these methods on our numerical model data. Here, this map is the elevation of the cycle base. This one is the elevation map of the cycle top, and this map is the difference between these two maps, and thus is the thickness of this cycle. Okay, now we apply the variogram analysis over this area, which is not too upstream, not too downstream. Then, interestingly, we see this long range of 22 kilometers in the azimuth of 0 degree, basically down valley direction. Then the short range is in the azimuth of 90 degrees, that's just the cross valley direction. And also, similarly, we find this Hall effect cyclicity patterns that we have observed in the field data. So now we observe similar patterns in numerical model data, also field data. That means the processes in these two datasets might be similar. Now we are going to explore the compositional stacking using this panel I have showed already in the previous slides. We use two metrics. The first one called CV, that's the coefficient of variation, and it can be numerically calculated as standard deviation over mean. For instance, for cycle n, that's top flattened. The CV is quite large because you see quite high values, also quite low values. But if you combine two cycles as one photographic unit, then it becomes much smoother. And also, given those thin and thick ones just direct on top of each other, so we may expect the CV to decrease as we combine more and more cycles as one photographic unit. Okay, here we show the result. As the number of stacked cycles increase from 1 to 6, the CV keeps decreasing, but after 6 it will not decrease anymore. So our predicted compositional timescale is here. We use another matrix called sigma SS. That's the standard deviation of long-term sedimentation rate over subsidence rate. But when it's fully compensated, then we see this nick point. So this matrix indicates a predicted TC of 7 cycles. But we have to highlight that much compensation is already happening in the first 3 cycles if you look at those values. We also want to have a look at numerical data. Here we have also 4 cycles. They are built by the channel stability phase. Then after this we have the washing phase. So you see those condensed timelines, they are very overlapped on each other. That means non-deposition of hiatus that are favored for the paleosoil to develop. Also here the cycle thickness is thin, but this one directly on it is quite thick. So one decompensational stacking is already happening here and also in the other places. So there are quite similarities between our field data and model data. Okay, now we have these take-home messages. First, the floodplain cycles, they can laterally trace it over a large distance, and the thickness could be allogenically controlled. These cycles also show lateral variability due to autogenic dynamics. Cycle thickness variation is most continuous in the paleoflow direction. Full compensational stacking occurs at 6 to 7 precision cycles, although most compensational stacking has occurred after 3 cycles. Okay, now thank you for listening, and it's time for discussion.